Okay, now it is recording. So I'm just going to share my screen as usual. You can always feel free to stop me midway if there's anything you wish to point out. You can always stop me and discuss and ask your questions midway. You don't have to wait until the end to ask your questions. Just going to put it in presentation mode, then we can start. So can you see my screen?
Yes.
Yeah.
Good. It's loud and clear. So also need to make a few people co-host, then we'll be. Okay. Okay, so here we go. So as usual, we will start with the problems. And for those who are here for the first time, this is Dr. James Katende. I'm from the Department of Mathematics at the University of Nairobi. And this is a training that we run every 2 weeks for the KKMO Kenya Mathematical Olympiad. So to discuss topics and typical questions that appear in these contests. So we have a total of 4 questions. I think we can start with the first one. This is just an appetizer. As usual, I give maybe about 1 minute for people to try it out and see if you can get any ideas on the way forward. But maybe I'll just read out the question. It says, Juma and Orina counted a lot of chicken and started bragging about it. So Juma exaggerated his amount by an extra 100%, and Orina exaggerated his amount also by an extra 600%. So altogether, they claimed the number of chicken is 3 times the actual count. So the question is, who counted more chicken and how many times more? So I'll leave the question on before we move to the solution so that people can get some ideas. If you get ideas before we move to the solution, please just unmute your mic and share. So hopefully there is no one called Juma in the meeting. So it's usually a good idea to have a pen or a pencil and some paper to test some of the ideas that will be presented here. It's also possible to come up with alternative solutions from what we have. The ones we present are just suggested solutions, and there may be several different possibilities. So when you have your pencil and paper, you might be able to come up with other solutions or even point out some errors in case there's an error in the solution we give. So is there anyone with any ideas on how to proceed? Even if you haven't got to the full solution, but you have a strategy, you can share the strategy. Okay, so should I move to the solution, or is anyone close to finding a strategy?
Okay, Daktari,
Yes.
I think I've gotten the solution.
Yes.
Okay, my answer is Juma by 4 times more than Orina.
Yes.
Okay, I just used algebra.
Yes.
Like the number, I gave the number of chicken counted by Juma as X and that of Orina as Y.
Yes.
Then I equated that to say Z.
Where
Then
Z is?
after, pardon?
Oh, that's the actual number counted.
Yeah.
Yeah.
Then I wrote another equation for the number after the exaggeration. So my
Yes.
to
Pardon?
3Z.
Pardon? Oh, that should be 3Z, yeah?
Yeah.
Mm-hmm.
Then after a bit of substitution, I was able to express X and Y in terms of Z.
Okay, that's exactly what we did. Maybe used slightly different variables, but that is precisely the solution that we have. So how we do it is this: we assign the number, we use J and T. Claren used X and Y. Yeah? So J for the number of chicken counted by Juma, and T for the number of chicken counted by Orina. This is before the exaggeration. So after the exaggeration, the number of chicken counted by Juma will be 2 multiplied by J, because he exaggerates his number by 100%. So what he reports will be twice the number that he actually counted. In the same fashion, Orina exaggerates his by 600%. So what he reports will be 7 times what he actually counted. But the total that they report is actually 3 times multiplied by the actual count, which is the actual count will be J plus T. So then if you manipulate this, you end up with J is equal to 40. So that means the number of chicken Juma counted was actually 4 times the number of chicken that Orina counted. Is this okay? Anyone with questions? I don't know if there's a simpler solution to this. I think this is just about as simple as you can get. Just making use of the knowledge of percentages and a bit of algebra, and be able to find the solution. Okay, so that was the appetizer. I think, thank you a lot, Claren, for giving us a solution. Turns out to be exactly the same one that we have. So here is a second question. It says 10 positive numbers are written on the board. All of their last digits are distinct. So all their last digits are different. That's what it means. That furthermore, all of their second to last digits are also distinct. Prove that the sum of these 10 numbers is not a perfect square. I think we all know a perfect square. A perfect square is a number like 9, for instance, because you can find an integer which, when squared, will be equal to 9. In this case, when you square 3, you'll get 9. So 9 is an example of a perfect square. There are other examples like any squares, perfect squares like 9, 16, 25, 36, and so on, 49, 64. All those are perfect squares. So the challenge here is to prove that the sum of these 10 numbers cannot be a perfect square. Again, we can give you a little more time to work this out. So ideally in the first and second round, we usually don't ask this kind of questions where you have to prove something. But in this training, I think it's a good idea to introduce this kind of questions so that people can walk away with a few more techniques than what they normally have. So again, we'll give maybe 1 more minute for anyone with ideas on how to proceed. Any ideas so far?
Just thinking out aloud.
Hello?
Congruence.
Pardon?
The use of congruence in that pairs are either congruent to 1 or 0.
I can't hear you clearly.
By use of perfects, by use of congruence in that pairs are congruent to 0 or 1 modulo 4, and then if they are 10, summing them up can either give you 2 modulo 4, which it gives you 2 modulo 4 or 0 modulo 4. In that, in the case when it's 2, then it's not a perfect square.
So how do you figure out the remainder is 2? Hello?
If okay, let's say if it's 1 modulo congruent to 1 mod 4, then at the end of it all, we'll have,
how do you determine that the sum? Okay, for some reason you are, I can't get you clearly. Am I the only one not getting in, or? Hello? Can anyone else hear him? I don't seem to be able to get him clearly. Or can anyone else hear me?
We can hear you, but his is not very clear.
Okay. Maybe he has some network problems.
Possibly.
Yeah. So anybody else with some ideas? He has some idea. It's a generally good idea, but using fairly advanced techniques. There's a simpler way to solve it. So I think I'll move to the solution. Or is there anyone who is close to finding a way forward? Not yet. Okay, so we'll move to the solution and try to explain. So we have a total of 10 numbers. So we arrange them vertically as you would if you are going to do long addition. And then we call the sum of all the numbers S. So let S be the sum of all the numbers. So we are given 10 digits and we are told that each of their last digits are different. So since they're different, they must all be 10 different digits. That can only happen if the last digits, each of the numbers from 0 to 9 will appear in at least one of the numbers, in whatever order, but they will appear as last digits for the numbers. So if you're using long addition and you add up all the terms on the right-hand side, then their sum will be 45. If you add the numbers from 0 to 9, their sum is 45. And as usual, when you're adding, you will write 5 and you carry 4. So the last digit of this sum S will be 5. Think we are together up to that point?
Yeah.
Okay.
Yes.
So the next thing is the second last column in that setup. Again, we're told the second last digits are all different. That can only happen again if all these digits from 0 to 9 appear exactly once in that column. We still, again, don't care about the order, but they must appear for the numbers to be all different if they are 10. So we add up all these numbers. Again, we get 45. We had carried 4 with us. So if we add 4 to 45, we will get 49. So when we do this, we get that the second last digit of S is 9, right? And therefore the last 2 digits of S are 95. So this is good information now. We can work with this. We don't care about the rest of the digits now. For it, we clearly can see that if it's 95, if the last 2 digits are 95, then it means S is divisible by 5, right? But S will not be divisible by 25. The only way if S is divisible by 5, for it to be a perfect square, it cannot have only one factor, 5. Yeah, they must occur in pairs. So here 5 occurs only as one factor because this number, if the last 2 digits are 95, it's only divisible by 5, but not by 25, and therefore it cannot be a perfect square, right? Are we together up to that point? So this
Yes.
proves that this sum cannot be a perfect square. So also by just looking at these last 2 digits, you can use the same arguments that it was Tito who was giving the answer. The same argument Tito was using. By just looking at those last 2 digits, you can easily conclude that the sum S is of this form, 4k plus 3. And therefore it cannot be a perfect square. Perfect square can either be multiples of 4 or they leave remainder 1 when divided by 4. This can be proved. I did not include the proof for that, but this is true. Any number of the form 4k plus 3 cannot be a perfect square, where k is a positive integer. So they can either be 4k or 4k plus 1. Also, if it was 4k plus 2, it cannot be a perfect square. But in this case, if it's a multiple of 5, it means, I hope this last part is clear. Do I need to explain more? Although the problem is already done, up to this point, the problem is already done. We've already proved that it's not a perfect square. So the additional bullet here is just using some more advanced techniques to check that it's not a perfect square. Any questions on this? Okay, so we move to the next one. So question 3. So question says, is it possible to split all integers from 0 to 303 into pairs in such a way that the product of the sums of the numbers in these pairs is a 15th power of some integer? So we have a total of 304 numbers here. The question is asking if you can pair them, and in each pair you add up you add up the numbers in each pairs, then you multiply them. So the question is, can that product be written as an integer raised to 15? So again, if you have any ideas, you can give everyone a few minutes to figure this out. So the trick is already given in the question, the pairing. So you have to figure out how to pair them so that the product will be a 15th power of some integer. Any new ideas? Fresh ideas to solve the problem? Again, if you get any ideas, simply unmute your mic and share. So again, I'll just restate the question. Basically, you have 304 numbers, you pair them, then add up the numbers in the pairs, then multiply the pairs, the sums, get the product of all those sums, and tell us if it's possible to write that product as some integer raised to 15. It's a bit of a puzzle, so you have to figure out how to pair the numbers. Anybody with some ideas? So is it getting too tough? We can move to the answer, or is anyone close to a solution?
I must admit, the question is a bit tough for me, but
Yes.
I think the pairs should be in such a way that the sum of numbers in each pair is equals to 303.
And then how do you do that? How do you work with that?
Now from there, I don't know. It's tough.
Okay, you just need one more trick there, and you're done. So, okay, I'll move to the solution. So the first thing we'll do is pair the two numbers 0 and 1. So the sum of this pair is equal to 1. So we can put that aside. So then we pick all numbers between 2 and 151, inclusive rather. So that means 2 and 151 are included. Now for each of these, there are a total of 150 numbers here. Or is it 151? 150. Is this correct? Yeah. So so we pair each of the numbers in here with this number 303 minus m, right? So the next number 152 will be paired with 151. Then 153 will be paired with the 150 and so on, so that each of the numbers in here will find a counterpart on the other side. So 303 minus m will be paired with m. So that gives us a total of 150 pairs. And the sum of each pair is 303. So if we multiply all these pairs, not really the pairs, the sums of the pairs, I think I need to correct that. So if we multiply all these sums, this first sum is just 1, so it will not have any impact. We can ignore it, but the rest will all be 303 raised to 150. So now this power is a multiple of 15. It means you can write it as 330 raised to 10 in brackets raised to 15, which is exactly what we were looking for. So the answer is yes, it is possible. And the number we are looking for is 330 raised to 10. That's the integer which is now raised to 15. There may be, if you think it through, there might be a few other ways to pair the numbers, but this definitely works. So this answers the question. The question was whether it is possible, and the answer is yes, it is possible, because we have found a pairing which works. Are there any questions on this one? So Claren, you can see you are one step away.
That was quite close, but yeah.
Yeah. Okay. We'll move on to the last
question.
Yes.
Are we allowed to pair distinct numbers, or we can pair also similar numbers, let's say 0 and 0, 1 and 1?
You have to pair, there are exactly 300 numbers, so you don't repeat any of the numbers, the pairing.
Okay.
You don't repeat any of the numbers. You just pick the numbers that are in the set. So once you pick one, you can't pick it again because it's already picked. So that's okay. So this is a final question for today.
should it have been 330 or is it 303?
303.
330 raised to power 10. I'm on 303.
It's a typing error. It should be 303. So the 3 jumped before the 0. So you're right. That's correct. You should change it to 303. Okay. So here is the last question. This one involves a little bit of calculation. So maybe I can give 2 minutes for this one, for anyone who has some ideas. So this question simply says we have a function, a quadratic function, and A is supposed to be strictly greater than 0, not greater than or equal to 0. It should be strictly greater than 0. I think this was a typing error also. So A is not allowed to be 0. A must be strictly greater than 0. And this function is such that it intersects each of these 6 lines in exactly 1 point or no points at all. So at most once, they meet at most once. So either it's a tangent or doesn't touch the curve at all. So under those conditions, you're supposed to find the maximum possible value of this ratio, C over A. So this one, you basically need to play around with the discriminants and a few ideas. Anyone with some ideas? Any ideas? Anyone with some some strategies that can work. Looks like this one is a bit strong, so maybe we should move to the solution. Anyone who is close to finding a strategy? Okay, so we'll move to the solution. Let's just go through the question again before we go. The question says we have this quadratic function where this a is strictly greater than 0. So I was supposed to keep this as strictly greater than 0. So it's not allowed to be 0. And we claim that this function intersects with each of these lines at most once. So at most once simply means the lines either touch the graph of this function, or they don't intersect at all. So the challenge here is to find the maximum possible value of C over A. So we start with this pair because we want to find the intersection, and the information we have is that they touch at most once or not at all. The reason I've picked this first one is because it has a C here and there's a C here as well. So when you equate them, the C disappears and life becomes easier for you. So when you equate them, we end up with the I skipped some steps, but you can check that this is true. When you equate them and simplify, this is what you end up with. And from this, you have two options. Either x is 0 or x is b minus a over 2a. Now, that gives us the impression that they will always intersect. These two, at least at 0, they must intersect. And if you want it to be only one point of intersection, we need the second one to be also 0. So the second one can only be 0 when b is equal to a. So we can conclude that b must be equal to a. That is one step we have made. So that is when b is equal to a, the intersection point will be 0, 0. Right? 0, not 0, 0. They will be at when x is equal to 0. Now, we consider another pair. So in this case, we pick this second line, ax plus b, just from the list of lines that we have. So before you eventually get to the pairs that give you good ideas, you will have tried the others as well. This one looks clean because it has been, all the rough work is done. So here it may look easy, but it may be necessary to play around with some of them before you get to the final selection. So when you select this and equate it to the quadratic function with the information that b is equal to a from the previous step, so we can simplify and we end up with this. 2x squared is equal to 1 minus c over a. Now remember, we want the solution to be either 1 point, the two to intersect at exactly 1 point, or none. So that means the largest value that c can, rather the smallest value that c can take is 1, right? So that if it is 1, we have exactly one solution. I think when x is equal to 0. Other than that, it must be greater than 1, in which case we will have a negative integer on this side, and therefore we can't find any real solution. That means there's no intersection between the line and the quadratic function. Am I making sense up to that point? So we must conclude that c over a will be at least 1, but it can't be less than 1. If it is less than 1, we end up in trouble because then we have 2 points of intersection, and we only want these lines to touch, either touch the curve or don't touch it at all. So they will touch it when, in this case, the two will intersect at 1 point when c over a is equal to 1. And therefore this whole quantity here will be 0. So at the intersection point will be when x is 0. And then if we pick c over a to be bigger than 1, then the result here will be negative, and therefore we can't find any real solutions. And therefore the line and the quadratic function will not intersect. So this any value of c over a which is greater than or equal to 1 will satisfy the conditions that we look for. Does that make sense? Can anyone hear me?
Yes, we can hear you.
Okay, that's good. So there's no quarrel with what I have done so far. Anyone? So we consider one more pairing. We pair this quadratic function with this line cx plus a. And if you divide throughout by a, so the reason we have picked this c and a is because now we know what b and a are, so we pick something that doesn't have b in it. So cx plus a equated to this quadratic function, you can divide throughout by a. Since a is not allowed to be 0, you can divide throughout by a. It will not affect the equation. And when you put like terms together, you end up with this simplification. You could try to verify that this is true. So this is just a quadratic equation. So for it to have at most one root, the discriminant must be less than or equal to 0, right? So if you compute the discriminant, this is what you end up with. So the discriminant is just the usual b squared minus 4ac. In this case, b is negative c over a minus 1. And what we would call c is c over a minus 1. So b squared and a is 2. In the standard, if you were to put the quadratic function in the standard form. So the usual standard form. So this is a discriminant. And for this to have at most one root, it means either the discriminant is 0, in which case it has one root, one repeated root, and if not, if the discriminant is less than 0, then there's no root, which means this line cx plus a does not intersect the quadratic function, which is fine for us because those are the conditions we have been given. So we want to figure out what happens here. You already have some information about C over A being greater than or equal to 1. So this, if this is either 0 or positive, the only way this can eventually be negative is if this second term is negative, right? And this second term would be negative if C over A is less than or equal to 9. So we have found a lower bound for C over A and an upper bound for C over A. So C over A, smallest value is 1, the maximum value may be 9. We don't know if it is 9. We have to check if it works. Can C over A actually be equal to 9? And the conditions given in the question still hold. That is the task. So we can check that when A is equal to B and C is equal to 9A, the three equations consider so far will have exactly one root. This should be one root. That is already guaranteed because they have been picked in such a way that this C is equal to 9A will satisfy this, where the equality holds. And A is equal to B has already been established earlier. For this, when this is true, all the three equations considered have exactly one root. So it means the maximum value should be 9 because you have confirmed that even at this maximum value, the conditions are still satisfied. The maximum value of C over A should be 9. Now you notice we have only considered 3 of the lines. So because of this condition, A is equal to B, the other 3 equations, if you make these substitutions, they will reduce to the ones you have already considered. So they won't give us any new information, and therefore we will not need to use them. And we simply conclude that the maximum value of C over A is 9. Because we have checked that when at that maximum value, all the conditions still hold. And therefore, we have solved the problem. This was a bit long, so I don't know if there are any questions. Are there any questions on this? But you can see the ideas being used here are nothing more than just the basic ideas from from algebra, the quadratic function. So we don't use any advanced ideas to solve this problem. They're just the knowledge of the quadratic functions, the discriminant, and knowing when when a quadratic function has a distinct, no real solutions, and when it has exactly one solution. There are no advanced techniques used. Are there any questions on this? So you can check this last statement where A is equal to B. If you go back to the question, so you see if A is equal to B, then this last one, this becomes these two last lines are the same exactly. So once you consider one, you don't need to consider the others. These two are also the same. The first in the top line and the first in the bottom line here, they will be the same since A is equal to B. And which other one? And these two also will be the same. AX, this second one and the last one here. will be the same because B and A will be equal under the conditions you have been given. We've seen that B must be equal to A for those conditions to hold. So once you check for the first those three equations, you don't need to check the others. They will not give you any new information since B and A are equal. There's a lot of silence. I don't know if anyone can hear me.
We can hear you.
Yes. Okay, so that brings us to the end of the talk today. If there are any questions, please feel free to ask. Also, if you have any suggestions, please feel free to chip in. So I'd like to point out that today we had some special guests. We have the technical team from Kenya Airways, the engineers, I think. Maybe they will want to say hello to the audience.
Hi, everyone. I just wanted to familiarize myself with what to do here.
Okay. Thank you very much for showing up. We really appreciate the audience. So anybody who has some suggestions on what we have done? Okay, so thank you very much for showing up. I wish everyone a great evening. We meet again in 2 weeks to solve a few more problems or discuss some topics in Olympiad mathematics. So I hope it was enjoyable for everyone. And I hope someone learned something new. And we hope you will be back again.
We have learned something new.
Okay. Okay, so I will wish everyone a good night, and we'll meet again in 2 weeks. Thank you very much.
Thank you.